So when you drop an electric dipole in an electric field, it turns or changes direction because the electric field provides the required force and therefore the torque for it to turn. And if the electric field is providing the force and the consequent torque, we can say that the electric field does work on the dipole. So let us try to find the work done by this torque when the dipole turns, let's say, by an angle alpha. But before we do so, also recall that just the way we say that work done in linear motion is the product of force and displacement, say x, in rotation the equivalent of force is torque and the equivalent of displacement x is angle alpha, and therefore the work done is torque into alpha. Well, things are not as simple here, since we can see that the torque is changing every moment as the dipole turns from position alpha 1 to alpha 2. And you know that torque is changing because the magnitude of the torque depends on the angle alpha that itself is changing every moment. So we cannot really put work done as some single known value of torque multiplied by alpha. So what we do is use integral calculus and try to add up the tiny magnitude of work that happens every time the dipole moves a very small angle between alpha 1 and alpha 2. So let's say that at some instant the dipole has moved an angle d alpha, where d alpha is very small. Then we can say that the work done is torque at this point multiplied by d alpha, or dw is equal to t times d alpha. Obviously here the assumption is that for very small change in angle d alpha, torque can be assumed to be more or less the same. We also know that torque is equal to minus P cross E, or this equals minus PE sine alpha. So we can say that dW is equal to minus PE sine alpha into d alpha. Now we can use integral calculus to find total work done between alpha 1 and alpha 2. So we can write total work done W is equal to integral of dW, that equals integral alpha 1 to alpha 2 minus PE sine alpha d alpha, and if you integrate it, what you get is this equals PE cos alpha 2 minus PE cos alpha 1. Now let us go ahead and write this expression as W is equal to minus, and within brackets, minus PE cos alpha 2 minus PE cos alpha 1. And we will soon see why we are writing this expression in this strange way. Now we also know that work done is equal to minus of change in potential energy, or W is equal to minus of U final minus U initial, where F and I are the final and the initial points. And in this case it is W is equal to minus of U2 minus U1. And if you compare this with the strange way we wrote this equation earlier, what we find is that U2 is equal to minus PE cos alpha 2 and U1 is equal to minus PE cos alpha 1. Then we can say that in a more general way, the potential energy at any point, say angle alpha, can be written as U alpha is equal to minus PE cos alpha. Or we could say that the potential energy of a dipole in an electric field is the minus of scalar product of P and E, or U alpha is equal to minus P dot E. So if you like this video, go ahead and give it a thumbs up, and please do not forget to subscribe to this channel for many more interesting videos.